So this is a variational approach, maybe one or two, maybe more than one variational approach to a very few stochastic problems, but I want to give an idea about how some of these things might be used in some of these kinds of problems and how they have been used, in fact. And one area that we look at this kind of problem, or might look at this kind of problem, is in the area of optimal control. And so here's so the classic deterministic without any probability and kind of optimal control problem where the idea here is that we have a functional, this J is a functional that measures maybe a cost of arising from some process, and we're going to control the trajectory of the x, right? X is a function of t, is by using some function from some given class of admissible controls, and the way that we're going to use the control is through this function will determine the dynamics of x that could be used, which is the state that gets plugged into the control. The control itself may contribute to the cost as well, right? Using the control maybe include some cost. And so we're going to try to minimize the cost by making a good choice of admissible controls. And this kind of problem is actually directly related to what we also refer to the more classical calculus of variations problem, where we're looking at a functional of some kind, and again a minimization problem, perhaps. But directly we're just looking for the path, and may depend on its derivative. The cost would depend on the time, the position, and the derivative, and may also actually both of these we also may have a particular cost of stopping the process. We stop the process, right? Where we are in the end may have a particular cost as well. And so if you just let this function just be x prime is call that u, then it's really the same process. So so in some ways the optimal control problem seems to be more general, but it turns out that there's also another connection we're going to talk about later, that the control problem can be framed in this calculus of variations problem with more dimensions and with constraints. So we can use constraints in the for a calculus of variation problem. Now, the calculus of variations is a very old kind of problem. It's used to solve some interesting problems in physics and other places. So and there are different ways of approaching it. And I'm going to talk a little bit more about that in a really very, very simple example to give you a sense of what it's like, what it's about. And the basic idea is that we can consider changing the functional by looking at taking the functional and let me go back in. So taking this function for the calculus of variation j of x. Ultimately, what we'd like to do is to modify that a little bit, and add a little bit of another function to it. So a lot of the time when we're dealing with these problems, many of the cases we're interested in fixing the endpoints, the values at the endpoints of an interval a and b. So we might make this additional requirement that the variation does not change the values at the endpoint. But other times we might be interested in more free variation. So altogether, these are the kinds of functions that we can modify the other function with, and we're going to try to figure out optimize it. And this is a point actually where I'd like to draw separate pictures. I didn't want to put together on here. But the idea is this: is I have a function x of t, right? So, and maybe I fix the values at a and b. And the idea is that if I already have the optimal such x for this particular cost, then what would happen is if I were to modify it a little bit by adding another function onto it, and actually adding a multiple of that function onto it, then what we expect to have happen is that now I do my other color, that my original graph, I need a better color. This might help, yeah. So the purple here is the original color, the graph that if I were to modify a little bit, I would still find that the best value would be, this value would be better than all these other values. And so if it's going to be the optimum, then as I change the input, the x that the function I'm looking at, when I change a little bit by epsilon, if it's actually the optimum, then we'd expect the derivative with respect to epsilon at 0 would be 0. We'd have a critical point in the epsilon. So we've converted this to a problem where we have possibly all these other functions, but it comes down to a problem of finding the derivative of just some of a real valued function, right? The epsilon. So we find the derivative with respect to epsilon, set it equal to 0, and that gives us a condition, a necessary condition that an optimal point would have to satisfy. And if you trace through all the derivatives you'd have to make on this, look at the lower function here. If you're going to take the derivatives with all the epsilons there, so epsilon would be x plus epsilon z and x prime plus epsilon z prime. Epsilon's going to occur lots of places in there. If you trace through all those derivatives using the chain rule, the result is this is what that derivative would look like, right? When I set epsilon equal to 0. So that gives me a condition. That gives me a kind of necessary condition where this would have to satisfy. Now it involves an integral on all these derivatives, but the next step is the classical step is integrate by parts, so that we have, and I'm not showing all this stuff, but so that we have for each z, we have z multiplied times this expression like this. And so this produces what's known as the Lagrange equation that must be satisfied when we have a critical point solution. In addition, so we get this equation by looking at all those possible variations z, a little bit looking at different z's and taking the derivative with respect to epsilon. But for different classes of z, with different boundary conditions, we can get some additional conditions. And in particular, we may specify the initial values at a and b at the endpoints, but we might not specify them. But there's a certain requirement that we get if we don't specify the values at the endpoints, which were known as the transversality conditions. So those would be additional conditions if we didn't specify the endpoints. So you might just start the process off somewhere and just let it run and see where it ends up, but they would still have to satisfy, if you don't specify where you're going to end up, you're going to have still this kind of condition. Especially if we have a cost at the end, that cost function is going to show up in the condition here. The corner condition also means that basically that it guarantees that to some degree this has got to be continuous. Again, by making the right choice of z, we can derive this kind of relationship. So here's a real simple example. Suppose I want to try to find x, a function that at A, it's equal to x of A, and at B, it's equal to x of B, and I want to minimize this functional, which is, I don't want the, the derivative to be too big, right? Well, maybe you can kind of guess what's going to happen, but the Euler-Lagrange equation translates into this equation. It's the derivative of x prime and the derivative of the partial of this functional with respect to x prime is really what we're looking for, right? Is just the derivative. The partial is just x prime. The derivative of that partial is the partial derivative is just x prime. The derivative of that partial should equal the partial with respect to x, which in this case there's no x at all in there, so that's just 0. And I get this simple requirement that the derivative of the first derivative, in other words, the second derivative, is equal to 0. So what's the solution? It's just a line from point A, xa to B, xb. So the straight line is the optimal solution. And that's not surprising because, in fact, along the line, this quantity x prime is constant, right? So as long it's so having a constant value means that I'm not going both up and down, right? And so by not wiggling it, it makes it smaller. Okay, well that's a very simple-minded example, but in some ways, but it's an example of how the method works. So what does this all mean in the stochastic situation? Well, so we might do sort of the same thing, and actually let me kind of jump to this part here, right? That before we had that the derivative of x should be given by some sort of function of the time, the position, and the control. And so here we're doing the same thing. We're showing that what this equation is saying is the differential form is saying this is sort of the derivative with respect to time, should be given by the control. But the other part of this is that we might also have noise that's generated by Brownian motion by some random process. And you know what Brownian motion in this case, standard Brownian motion is it's something. Well, I can't really draw it because it's nowhere differentiable, but it's constantly wiggling, and it's a Gaussian process that is normal, and it's going to satisfy this kind of relationship that the average value is 0. This is the sum of the relationship that satisfies. The variance then is proportional to t. So that means that as time goes on, it could be farther. It could have wandered farther, right? And close. But it's also true that the increments also satisfy a relationship like this. That is, if I go from here to there, it kind of reproduces the same behavior. Whenever I start it over again, it reproduces the same kind of behavior, where with this Gaussian mean 0 independently, Gaussian mean 0 and variance dependent on the time. So there's a type of integral that we could define in terms of this, which really would tell us exactly what this means. But you can think of this as just sort of a white noise term, right? It's the increments in the Brownian motion is just very random. So we add randomness to this process, to the trajectory that we're looking at. So we take this, we have this situation. The control might affect the randomness, might affect sort of how it changes with respect to t. This generates a trajectory, which now we put it back into our functional, and we'll get some sort of cost. Now, one of the problems here is that because this is only random, and in fact, because it's Gaussian, right? There's some probability that it's way out of the tail somewhere, right? So there could be a very wide erratic sort of movement of the position trajectory. So in general, we don't expect to be able to get any kind of consistent value for the cost unless we average. unless we take an average. So here this E refers to expectation. So we look at the expected cost, or that's the typical traditional way of looking at stochastic optimal control. And so the problem then again is that we're going to look for appropriate functions that when we make the right choice of the function, the resulting trajectory produces x along with that u produces some sort of minimization of this expected cost. I don't doubt the minimization, but it minimizes up there. So we add this. We have to look at the mean of the expectation in order to make sense of this without some other kind of consideration. Okay. Anyway, that's the traditional approach, and there are various methods for solving these kinds of problems. But I want to look at kind of another way we might look at this problem. And so what you'll see that's really different about this way, and first of all, I made it a bit simpler. I made it more like my calculus variations problem, where the part that depends on time, the derivative with respect to time, is just u. I haven't done a lot about this stuff in there. So that's sort of like the derivative, except that there's also this noisy term that's adding noise to the whole thing. This was the randomness that's being added into it. Now I'm looking at this functional. Of course, what I just said is that I put this random process into here. This functional could be pretty wild, right? We don't really expect to get kind of any consistent value. And if I don't take the expectation, I'm not going to smooth that out. So that seems not necessarily very practical. But we'll see how we can get around this. And the method here, so we don't taking the expected cost. We're just looking at a cost for each trajectory in some way. We will have to. The kinds of variations I'm going to look at are going to be limited to begin with, and so we're looking at kind of the calculus of variations version where u and x prime are really kind of the same thing. There is no real x prime in this process, though. Such a process has no derivative. So the next best thing we have to x prime is the function that controls the drift part of this equation, the part that just depends on the passage of time, right? Or this depends on relative to time. At the same time, so we have this part that's kind of like the derivative, but this other part is crazy noisy and not differentiable at all. So, okay. Well, given all that, it's still possible, though, to use the space HAB, right, of the variant functions that go from that are defined, that are they're absolutely continuous. Their derivative is at L2. We may restrict them to be certain values at the end, but we don't necessarily have to. We can look at this class of functions and still look at the same thing we did before. Look at a variation for this process, and the things that are going to happen with this variation are that we're going to plug that in. When I take the differential, the trajectory is going to be composed of, it'll be the same variation, will be the u will be modified by multiple of z prime, while the x is modified by multiple of z. So it's performing just the same way as the other problem, except that all along the variations are also going to be subject to this additional noisy term, so that they'll all be random as well. But I can calculate this integral. Now this integral is still, and this in part is it's still going to be random, but continuous, and as long as the f is nice enough, right? It's all continuous, and so we can actually then and the derivative of this functional, with respect to epsilon, evaluated epsilon to 0, can be computed, and we can set it equal to 0. So all I'm really claiming here is that what I have here is I have a process that's being driven by the U, which is performing in kind of the ordinary calculus sort of way, like x prime. It's also got this other noise thing going on, but in some ways I'm only doing the variation in the U direction. It's really kind of like a directional derivative. I'm only considering the U part of it changing and not the noise part of it changing. And, well, so by setting it equal to 0, we're getting some kind of partial critical point, but we're not really not making any claim that this is really a minimum or maximum or anything else, because the noise is doing its own thing, right? But the thing is that by looking at just this part of it, we still would expect, as long as when I have my noisy process, so now instead of a kind of smooth process, the whole thing is all noisy, but I'm adding a variation in the same way, I would still expect that it'd be interesting to look at those cases where that process is critical relative to all the possible variations of it. It's a critical point. And nothing else. I get a condition. And so the first part of this condition that I get is, like the Euler-Lagrange equation, is the differential of the partial with respect to the U component has got to equal the partial with respect to the X component. And there's also the original trajectory equation. So if I have a critical point of that type, these equations have to be satisfied. If I have a critical point of this type, I have similar sorts of transversality conditions and corner conditions that have to be satisfied. So if I look at my simple-minded, what was kind of a simple-minded problem before, it's not so simple-minded anymore. Well, maybe, let's see. So if I have the same kind of functional here, where it's basically like x prime squared, except there is no x prime, but it's the U, the control. And I have my trajectory that's driven by, here, just a constant multiple of the white noise and the U. And if I fix the values of the endpoints, the Euler-Lagrange equation tells me that the differential of U should be 0, right? While the trajectory equation is still being satisfied. And I wanted these endpoints as well. So the fact that the differential of U is 0 means that it should be constant with respect to time. And therefore the x should be it should have this form, because it's U is just a constant. And so if I integrate it, I'm going to get the integral of dwt is wt, and the integral of dt is t, right? So I get my trajectory the way it should look. And in particular, in order to guarantee that the endpoint conditions are satisfied, that constant has to look like this. Okay. So what's interesting about this is that this has, in part, this noisy term looks kind of like Brownian motion, but then there's this other part. This, W1 is fixed. But the problem, the unusual thing about this is that as a control problem, it's maybe not very reasonable in a way, because usually we think of the control problem as depending on, we're making the control based on what we know right now. And here I'm saying you have to make the control based on what you know at the very end. Right? So somehow you have to look into the future in order to figure out what it should be. And so we call this anticipating. We're looking at information that we don't really have access to at time t, but that's exactly what's coming into the control at this point. Okay, well, that may seem like it's kind of maybe not so useful, but it turns out it's not such an unusual thing. For example, you might have you might think of something like a stock price, or something that, or some simple kind of thing that's being changing because of noise in the environment, and suppose you observe at time 0 where it was, and at time 1 where it was, right? But you kind of wonder what happened in between. Well, maybe for modeling purposes, you'd like to know what happened in between. Well, if you have that information, you could still say, well, maybe it's something like this, even though, because now you know what. So going backwards, you can say it might have looked kind of like this, and therefore we could use that as kind of a fill-in for what what it might have actually been. And that's actually used for modeling purposes. This idea with this anticipating solution. It also turns out that if we just look at it the right way, if we use a different Brownian motion, this might actually be the same. We might be able to do the same thing with the penned values at the endpoints. So this is one version of Brownian bridge, but what it is not adapted to the Brownian motion. In other words, it's involving more information at time t than you would know from the Brownian motion at time t, and so that makes it limited in some uses, but it is in fact used. Okay. So we like to try to correct that, maybe, is that how can we take this idea and make it work so that it's actually adapted? And I would say that there is a minimization going on here in the sense that that every one of these paths, this kind of constant would have to be the minimizer. So. The other advantage, one thing about this solution is that we have, so I told you it's anticipating. It involves what happens at the end. But if you look at the path as a whole, if you know about the path as a whole, you can write down the solution as a function of the whole path from time 0 all the way to 1. So here's a second example. It's just a little different. It's actually a little bit more complicated in a way, but a little easier to work with. Because again, I have a functional that depends on u, and now here also, so this is the integral of the u squared, but also I have this cost that's attached to the value at the end. And again, it has a random trajectory. Stochastic trajectory, so to give the starting point, and these are all constants in there. The Euler-Lagrange equations look very similar, right? Because it's a trajectory, and then this part is just 0 again, so it's really the same one. But the fact that we've specified the beginning point, but we haven't specified the end point, and that gives us a transversality condition that has to be satisfied. So those two together allow us to solve the system. But now we have a situation where we can actually separate in some way partially separate the solutions. That the x has a starting point. We look how it evolves forward, and the u has well, we have an end value here from the ub, right? xb is given, but whatever the end of u, we have an end value for u that's determined by this. And so we have a place at the end that we can try to work backwards and find the solution. So if we don't worry about it being the fact that we're looking ahead, these are the solutions we get. And you see, again, well, here the end values of the Brownian motion is involved all the way down. So, but we get an optimal solution. This is constant relative to time. We have a random solution here that depends on looking ahead, right? So it's anticipating. And the transversality condition does push, just like the endpoint condition, the transversality condition pushes the value of WB into the solution somewhere. That's what gets it there. But could we find an adapted solution for something like this? Could we find something that doesn't depend on looking ahead to solve it? And so this idea was developed some time ago. Maybe 25 years ago, had a couple of forward-backwards system. And the idea is this. I can try to find and solve the solution, but since the U is not really right, it depends on that end condition, we might, however, try to solve, find another solution for u that is adaptive. And so we can think of it as sort of conditioning on the current position. So f sub t here represents the what we know up to time t. And so if we condition on what we know up to time t, that would give us an idea. But in particular, if it were adaptive, though, it's also true that it would have to have kind of a form like this. There would have to be an Ito integral of this type. So, so if we could find, so the other thing is, we'll find the v that will give us a u, which will be basically then the conditioned u, based on what we know up to time t. And if you remember, let's see, the transversality condition here says that u sub b should be equal to negative r x sub b. Right? If I use that, if I could use this value right here, I might guess that the u then should have this form, that it's some function of t times x of t, where that function is negative r, so that at b, u sub b is equal to negative r times x sub b. So that's a guess. But if you do that, we can actually solve. First of all, we can figure out what the u star has to look like. And then put that into the equation and solve to find what the x star is. Now, what we see is that this satisfies the initial Euler-Lagrange equation, but it also has this adapted. It's adapted in the sense that, well, it only in terms of the Brownian motion, we just know that you have to take the integral up to time t. Integral up to time t. We don't look in past t to know what's going on time t. So we can find the right kind of solution there. And then, in that case, if we use these solutions, then we can calculate the minimum random functional. So there's, and actually, the expectation of that. So we can figure out what that would be. And here's what we get. It's just a calculation from putting that back into the function. And I'll repeat it again up here. It is actually not as small as what we got when we had anticipating. But you know, that's also reasonable, right? Because if you look at the function, if I know everything up to time b, I ought to be able to do a better job than if I only know up to my current time. So that control doesn't, the adaptive control doesn't do as well at minimizing the functional, and we actually have to see it in this case that it doesn't. But that's not surprising. However, the mean that we got for this adapted version is exactly what we get from the Hamilton-Bellman-Jacobi methods for solving stochastic control problem that we had before. So we're really getting the same answer, right? So. I haven't talked about the Hamilton.